And the announcements you've heard before, Mr. Gerasi is forming and meeting with the math team. If you're at all interested in participating, I talked with one of the students who was in it in my yesterday morning's class. He said they're having a lot of fun and learning a lot of math at the same time, and it's really helping him out in his course and future courses, which he doesn't even realize yet. So if you want to do that, Fridays at noon, Birmingham West Campus, the C building, which is Science Building, C100, and then Monday at 3, same place. All right. They have tutoring going on here on this campus, down the hall here in Student Support Services, and then downstairs from there in the Space Center. It's free, and both places on the Birmingham campus, they also have the STEM lab, in the D hall there that has some tutoring. So lots of opportunity. Now, I would say for you guys, it's an opportunity for you to tutor, okay? They pay fairly well, I think a little bit better than minimum wage, and you set up the schedule exactly when and as often and as infrequently, whatever it is you want, set it up for yourself. And frankly, that's how I learned math, by helping other people, because when you have to explain it to somebody, it's a little bit deeper than just doing the problem. You have to sort of know the procedure and why and that kind of stuff. So really, that's where you learn best. So if you want to participate, please check them out. Okay, and then the one last announcement. I'm almost embarrassed to say I'm normally on the Birmingham campus on Fridays from 7:45 to 11:45. Seems like this term it's been more Fridays I haven't been there than those I have. I had 3 transfusions in a row. I had a meeting, professional meeting I went to, had another transfusion last weekend, and then this weekend, my annual physical. So I'm not going to be there again this weekend. But next Friday, as far as I know, I'll be there. Okay. But just letting you know. Now, we do have some sort of meeting scheduled for later on Friday. If I finish with the physical in time and can get over to the Birmingham campus for the meeting, I may be over there for that, but I won't be in my office even then. So I might be, if I get there a little earlier or something, I might be in the office for 15, 20 minutes or something like that before the meeting begins. But I can't say that now because I don't know how long the physical is going to take and how involved it will be. Okay. Yeah. Now, I'm starting here in Chapter 5, 5.2. We didn't quite finish 5.1, but the slides weren't on that, so I said I'd go on and set up from the slide here. We'll do this on 5.2. We have 2 more examples to do here. Okay. And the first of these is at the top of page 3. Before we get started, any questions on anything we've done so far? Okay. And I see. If I haven't gotten your first test in, please be working on those. I think I've got them. Well, maybe not for everybody. Okay. Yeah. Just whenever you can get it to me, because you already got the second test. And I did give Shanika her copy, and I had Cameron scanned and sent to him. So I hope he's got his too. Okay. So, top of page 352, example 8. This is chapter 5, analytic trigonometry, 5.1, using fundamental identities. So, here's one. It says, use this substitution. Okay, let me get my pen set up. All right, here's the substitution. X is equal to 2 times the tangent of theta. Now, they give you what the substitution is. In real life, most of the time, you have to come up with this on your own. But they're giving it to you here because it's your first time. Okay, this is good for any theta between 0 and pi half. 0 less than theta less than pi half. Okay. Now let's just pause a minute and think about that. Normally, tangent is good from negative pi halves to pi halves. There is a reason they're limiting this to just 0 to pi halves, but basically you're in the first quadrant. Why do we limit it to pi halves? Why don't we include pi halves in it? Yes, that's your vertical asymptote. Tangent is not defined at pi halves. So that's why we have that only up to but not including pi halves. You'll see in a minute why we are eliminating it. Oh, limiting it to greater than 0. Okay? So there's the first part. Okay? And what we're wanting to do is to write this expression. We're going to use that to write the square root of 4 plus x squared as a trigonometric function of theta. Okay? Now, you might say, what? Why? This is sort of a made-up problem. No, it isn't. Remember, this is pre-calculus trigonometry. In calculus, especially in Cal 2, when you're doing integration of various kinds, techniques and things, this kind of a function is impossible to integrate in this form. Okay? Absolutely impossible. But with that kind of a substitution, it becomes quite easy to integrate. So we're going to use that substitution to change this and make it a function of theta. So what would we do? That's the x squared. My square doesn't look very square. It looks like a 2, but let me clean that up just a little bit so it won't be ambiguous. Okay, that's a little bit better. So what's the first thing we got to do? Well, you got to square the x. So if x is equal to 2 tan theta, what is x squared? If x is equal to 2 tangent theta, what is x squared? 4 tan squared theta, right? Square the 2, square the tangent, right? All right, so there we got the x squared. Now let's add 4 to it. 4 plus x squared would then be 4 plus 4 tangent squared theta, right? You just add 4 to it, right? Now let's take a square root of that. And we'll have exactly what we're looking for here. Well, when you take a square root of that, what's one thing you see you can do to that? What's your F word? Factor. Can you factor anything out of that? I think you were saying it. 4. Factor out of 4. Okay? And what's the square root of 4? 2. So we'll factor out the 2. And what does that leave you with? Factoring a 4 out of 4, you get 1. No, you're factoring out a 4 out of the square root. Okay? Then you take the square root of 4 to get the 2. So you're factoring out a 4. When you factor that out, I should probably do 2 steps, shouldn't I? Okay, let's do it this way. All right. I get a little carried away. What this becomes is the square root of 4 times the square root. Well, wait, let's do it this way. We'll add yet another step. Okay? Okay. It's going to be the square root of 4 times what? Factor out of 4 from each term. You get 1 plus tangent squared theta, right? Okay, now that's a product. And we could write that as the square root of 4 times the square root of 1 plus tangent squared theta, right? Okay, what's the square root of 4? 2. The square root of, now what is 1 plus tangent squared theta? Sounds like an identity to me. Which one? If it's squared, the good chance it's going to be a Pythagorean identity. And what's 1 plus tangent squared? Secant squared, exactly. This times the square root of secant squared theta. But what is the square root of a secant squared? Secant. There we have it. This thing here is equal to 2 secant theta. Ha! Now, whereas this is an almost impossible thing to integrate, that's a lot more possible. Okay, it's not as easy as you might think, but it is something that's doable. Okay, so sure enough, that's what you've written that using a substitution, written that form in x squared, which is an impossible form to integrate into a form of theta, function of theta, which with a little bit of work is integrable. Okay. You don't have to worry about that yet, but that's what you get 2 secant theta. By the way, there is a checkpoint there, and that's well worth your time to do that. Now, they also have a figure here, and that was useful in example 8. And this shows where that's talking about. This is your substitution, right? That can also be written as tangent theta is equal to, if you divide both sides by 2, x over 2, right? Right? Now, in terms of opposites and adjacents, what is tangent? Opposites, adjacents, and hypotenuses. Opposite over adjacent. So if you drew your little triangle here, and it doesn't have to be precise or anything else, just make a right angle in there. Let this be your angle theta. The opposite side, if that is a right triangle, would be x, and the adjacent side of 2, right? Now, what would be your hypotenuse then? Two squared, which is 4, plus x squared. That's exactly what the original form was, wasn't it? And this thing then winds up being 2 times secant theta. Well, secant theta is adjacent, hypotenuse over adjacent. So 2 times secant theta would be that, and there's that point. So you see, your little triangles will be helpful in figuring out relationships, and pictures are worth thousands of words, okay? It hopefully makes it a lot easier to see. Okay. Now let's move on to example 9. Can I erase 8? Okay. Rewriting a logarithmic expression. So what they want us to rewrite is this, the natural log of the absolute value of cosecant theta. Woo! That's the absolute value sign. Plus the natural log of absolute value of tangent theta. Okay. As a single logarithm and simplify the result. Okay. Now time out a moment here. Why do we need to put absolute value bars here? Because you can only take logs of positive numbers. You can't even take the log of 0. Okay? So you have to have absolute value because cosecant, can be positive, but it can also be negative. You can't use any of those, or if you do, you have to take absolute value of it. Now tangent can be either negative or positive, and it can't be 0. Cosecant can't, but tangent can. So you have to exclude that value too. But that's why you have to have absolute value bars set. Okay. Now, it says rewrite this as a single logarithm. Do you remember any of the rules for logarithms? You probably only had a very brief time in 112, right? Okay. This is a new edition, I can't remember where they put their stuff. I don't think it's at the beginning, so it must be at the end. Here's some algebra. The very back thing, I don't see any logs there. Formulas from geometry and trig. You know, I don't see them anywhere. Okay. So the log chapter, I guess the place to go then, is chapter 3, I believe it is. Yeah, exponential log functions. Okay. Now, we'll look for the most concise way of expressing this. Thought it would be there. Ah, here they are. Properties of logarithms are in 3.3. So let's turn till we get near the end of that. Boy, they don't really, yeah, there it is. Okay. On page 220, properties of logarithms. Now these can be log logs or ln logs. They have them both listed there. Okay. Now, you see that very first one on 220, number 1, but go to the upper right, go across from number 1, and you see that log of u plus log of v is the same as log of u times v. Okay? But, also notice on number 2, the log of u over v is log u minus log v. Okay? I think those are the two we'll need. Okay? So, here's what I suggest you do first. And this is sort of a rule I'm going to use a lot. If I can't think of anything else to do, I think you've heard me say it before, you're going to hear me say it over and over and over. If you can't think of anything else to do, get everything in terms of sines and cosines, and maybe something will come out. So let's see what this will be. This will be the log of absolute value. What is cosecant theta in terms of sines and cosines? Good old reciprocal identity. You know that one, don't we? Cosecant is? A little louder. Okay, and what would it be if you had done reciprocate that? Opposite over hypotenuse, what would that be? Sine. So this is 1 over sine, right? Okay, so that would be 1 over sine theta. And we'll keep the absolute value bars there. You could just put them down here with sine. That would be fine too. I'll just leave them where they are. Plus the log of, and what's tangent theta? Sine theta over cosine theta. That's a ratio identity. Okay? Now, if you go back to the sum of two logs would be the log of their product. So that would be 1 over sine theta times sine theta over cosine theta. Right? But see here, the sine thetas divide away. Sine over sine is 1. So this gives you the log of absolute value, 1 over cosine theta. And what in the world is that? What's 1 over cosine? Secant. So that would be the log of secant theta. And what did they ask you to do? They asked you to write that expression, which is a sum of 2 logs, as a single logarithm. There it is, a single logarithm. Okay? And it says simplify the result. I think we've got it as simple as you can make it. And there's a checkpoint with an audio-video solution there. I would definitely give that a shot. Okay? Now, that finishes 5.1. Let's us do the vocabulary. Fill in the blank to complete the trigonometric identity. Sine u over cosine u is? Tangent u. Got it. Number 2. 1 over sine u is? Second. Cosecant u. Exactly. 1 over tangent u is? Cotangent u. Secant of pi halves minus u would be the same as? Cosecant u. Exactly. Sine squared u plus cosine squared u is? 1, always. And sine of minus u is? Negative sine u. That's because sine is an odd function. Okay. So homework exercises here. Do any of the odds, 7 through 11. All of those odds are at calcchat.com, 7's at calcview.com. Do any of the odds 13 to 18, they're all at calcchat. Do either 19 or 21 or both, they're both at calcview.com, calcchat.com, 19's at calcview. Do any of the odds 23 to 31, they're all at calcchat. Sorry, 25 is at calcview. About this time of morning, I just start running out of energy. That's that fatigue. I'm sorry. Okay, then do any of the odds 33 to 39. They're all at calcchat. 35 is at calcview. Do 41. It's at calcchat. Do any either 43. Wait a minute. Any of the odds 43 to 47. They're all at calcchat. 43 is at calcview. Do number 49 is at calcchat. Do 51, it's a calcchat. Do either 53 or 55 or both. They're both at calcchat. 53 is at calcview. Do 57, it's a calcchat. Do 59, it's a calcchat. Similar to one we did in class. Okay? Then do either 61 or 63 or both. They're both at calcchat, but 61 is at calcview. And then the thing we love to hate is friction. It's a calcchat, not at calcview. And then 67 is a true-false. Hopefully it's a calcchat too. 69 is a calcchat. 71 is an error analysis, which shows something that's totally incorrect, and it's asking you to figure out why it's incorrect. I hate kind of they do that because I'm afraid you'll look at that and it'll get embedded in your memory and you'll think that's an identity, and it's not. And 73 or 75 are both writing type things. All right, so now let's move. Oh, I'm so sorry. Goodness gracious, I feel like someone opened the spigot and I got drained. Just totally. I was a little bit this way at the end of my other class. That's why I was going to my office to get a swig of Dr. Pepper just to give me a boost. It wore off. Okay. All right, 5.2 is in Chapter 5, Analytic Trigonometry. And what we're going to be doing in 5.2 is verifying trigonometric identities. Okay? Before we go into that, and the only objective is to verify trigonometric identities, the name of the section and the objective. Okay? Now, a little bit of introduction here. It's a reminder. In this section, we'll study techniques for verifying trigonometric identity. What is an identity anyway? It's something that's always true no matter what the value you put in there. Now, it looks just like an equation, and I guess technically it is an equation. It's got an equal sign. But most of our equations we've worked through any time in math up till now, not all, but most, have been equations that are true only for some values in the domain. For instance, if you have this equation here, that's an equation. That's not an identity, because this is only true for certain values of x. What values of x would that be? Give me a few. X equals 0, sine of 0 is 0, right? But if x equals pi, it's 0. 2 pi is 0. 3 pi, 4 pi, 5 pi. Negative pi, negative 2 pi, negative 3 pi. So any of your n pi or n is any energy. That's true, but it's only for those. Sine of pi halves is not 0, it's 1. Okay? So this is a conditional equation. It's true only for certain values of x. For instance, x equals n pi. So there's more than one. Infinite number of times, where n is any energy. Okay? When you find those values, you're solving an equation. And those are the values that make that equation true. It's not always true. It's only true at certain values. That's why it's called a conditional equation. Now, something that looks just like that, it has an equal sign and things on either side. But this one happens not to be an equation. You can't solve that because that's true for every value x. Okay? Because sine and cosine have no limits to the domain, so that's true for any value x. This comes from sine squared theta x plus cosine squared x is always 0. That's an identity. It's not a conditional equation. It's true for all values of x. So therefore, it's an identity. All real numbers x, it's an identity. So that's the difference between an conditional equation, it's only true for certain values, and an identity, which is true for all values. In this section, we're going to be dealing basically strictly with identities. And we're going to be verifying. You don't solve them, you verify them. Okay? Now, what do we mean by that? We use other identities to try to simplify the ones given and see if they are indeed true. So that's what we mean by verifying. We're not going to be solving. So therefore, some of the techniques we used to use to solve equations, you can't use in verifying identities. Okay? So we'll talk about that. So verifying trigonometric identities. Although there are similarities, verifying the trigonometric equation is an identity. Verifying that a trigonometric equation is an identity is quite different from solving an equation. There are no well-defined set of rules to follow in verifying trigonometric identities, so it's best to learn the process by practicing. However, there are some guidelines that will help you. Now, let me say this up front. Okay? An identity looks like an equation. You have something on the left equal something on the right. And that looks like an equation. In solving an equation, we manipulate both sides of the equation. We go across the equal sign and stuff. Verifying an identity, you never cross the equal sign with an operation. You don't add or subtract the same thing to both sides. You don't multiply and divide the same thing. You never cross the equal thing. You can operate on this side, or you can operate on this side, or both sides, but never cross the equal sign. In an equation, you do. In verifying identities, you don't. So, their first thing is work with one side of the equation at a time. Now, don't stick to that. Sometimes I'll do them just make sure you don't cross the equal sign with an operation. It's often better to work with the more complicated side first. Okay? You can do that, but you can also, as long as you don't cross the equal sign with an operation, you can do them simultaneously, and you'll find I do that. Look for opportunities to factor an expression, as long as you do it only on one side or the other. Don't move terms over to, no, don't do that. Do factor the expression. Add fractions only on one side. You don't add on both sides. Square a binomial. Take a square root, whatever. Create a monomial denominator. Yes, that's a great technique to do. Okay? Look also for opportunities to use your fundamental identities. Okay? Note which functions are in the final expression that you want. Sines and cosines pair up well. Secants and tangents pair up well. Cosecants and cotangents pair up well, especially in your Pythagorean identities. Okay? Now, if the preceding guidelines do not help, then try converting all terms to sines and cosines. I think I've told you several times already, that's my go-to. Okay? Now, first look and see if anything else will work, but if I don't see anything right off the top, I get everything in terms of sines. Now, this last thing, always try something, okay? If it doesn't get you where you want to go, forget it, try something else. But sometimes just trying something will lead you, oh, wait a minute, I could do this, you know. So if you just throw up your hands, you probably don't go there. Even making an attempt that leads to a dead end might provide insight. Oh, but I could change that slightly and do something else. So we'll see some examples maybe of most of that. Verifying trigonometric identities is a useful process when you need to convert a trigonometric expression into a form that is more useful algebraically. That's why we do it. Okay? If you're trying to solve a trigonometric equation, and it just looks way too hairy, then don't try to solve it yet. Simplify it, okay, to come up with a simpler trigonometric expression. You do that by verifying identity, working with the identity. When you verify an identity, you cannot assume that the two sides of the equation are equal because you're trying to verify that they are equal. So when I do this, I try to always put a question mark to remind myself I'm not setting these equal to each other. I'm trying to see if they are equal to each other. As a result, when verifying identities, you cannot use operations such as, this is what I said at the very beginning, adding the same quantity to both sides. Don't ever cross the equal sign with an operation at all. Don't do it because that's not legal in verifying. So here's a fairly simple one, they say anyway. Verify this identity. Secant squared theta minus 1 divided by secant squared theta is equal to sine squared theta. Okay? Now, if this were me, and I guess it is me, I put a question mark in it because I don't know if that's true or not. All right, now there's several directions you can try to go here. What would you do to try to simplify? Verify.
I'll use the sign.
Yeah.
Multiply both of them by the denominator.
Okay, both sides of the equation. That's something you can't do. You don't ever cross the equal sign. You're only going to work with one side or the other. Which side do you think you ought to work with?
I meant like multiply like the top and bottom by the denominator.
Okay. All right. I think I've got what you're talking about now. Jared's here. By the way, we're on we're in section 5.2 on page 356 doing example 1. Okay. Now, you said multiply the left-hand side by the denominator? That just makes it a little more, it's a legal thing to do, multiply top and bottom by the same thing. That is legal to do, but it just makes it a little more complicated. Okay, now, I can think of several approaches to this. Give me another approach. Okay, that top looks basically, I think it's almost exactly a Pythagorean identity, isn't it? Which one is that? Okay, let's see. Tangent squared theta is what I think it is. Here's how I'm going to verify that. Okay, because I tend not to have these memorized. I just know that they look pretty. Remember that sine squared theta plus cosine squared theta is equal to 1. And to get a secant squared theta out of that, we need to divide by cosine squared theta. So divide this by cosine squared theta, divide this by cosine squared theta. And sure enough, there's your tangent squared theta. Plus 1 is equal to 1 over cosine squared is secant squared, okay, which is what we had here. And then if you subtract 1 from both sides of that, now that's legal to do, you get tangent squared theta is equal to secant squared theta minus 1. See, I don't memorize well, so I do this. And maybe it's not efficient. But sure enough, that makes that numerator tangent squared, okay? So this will be tangent squared theta. And that's one to look at. When you get squareds in there, see if a Pythagorean identity will help. Tangent squared theta over secant squared theta. Okay. We don't know, but we're trying to see if that's going to equal sine squared theta. Okay. Now, at this point, I go to my fallback. When I can't think of anything else to do, I get the left-hand side in terms of sines and cosines. And what is tangent squared in terms of sines and cosines? That's sine squared theta over cosine squared theta. Okay? Now, let's go on and put it over. What's secant squared theta in terms of sines and cosines? 1 over cosine squared theta. Okay? Now, what Daniel was suggesting right off the bat was multiply and divide the same thing, or multiply the same thing numerator and denominator, which would be cosine squared. That will go out and that will go out. And guess what you have? Sine squared theta equal sine squared. Yes, that's an identity for every value of theta, so therefore, yes, we have verified the identity. See it? Now let me show you another way. I'm not saying this way is any better, but it's just another way to do it. Okay? Now, if you notice in one of the guidelines, I'll go back to that, this one right here is create a monomial denominator. Well, guess what? This one has a monomial denominator. So you might be able to use that. So let's go and look at this. Now this is just an alternative way. You want me to use a different color? What color? Green. Okay, green, green, it's green, they say, on the far side of the hill. Okay, we're going to split this to be secant squared theta over secant squared theta minus 1 over secant squared theta. Right? That you just split that into two different fractions because you had a monomial denominator, right? Just the opposite of subtracting fractions is unsubtracting. Okay. Now what's secant squared over secant squared? 1. Okay. And what's 1 over secant squared? Get to know them. What? Cosine squared. Now, what's 1 minus cosine squared theta? Sine squared theta. There it is. Left-hand side equals right-hand side. Second? I think that's a little easier. Okay? But if you don't see it, the other way works fine too. See, in both cases, you use the Pythagorean identity. This one's a more familiar one, but sure enough, this was one too. Okay? And then you got it in sines and cosines. Well, we split the fraction first and got it in sines and cosines, then used the Pythagorean identity. So, yeah, both of those work, and you get the same result. You see? Make sense? Okay. So, if you don't like cats, there's more than one way to skin a cat. Okay, but you don't need to skin cats. Okay. All right, there is a checkpoint there that you can verify that one as well. Okay? Let's see which way they use. We'll erase all this. Is okay to erase? Okay. See which they used. Oh, man. They use a Pythagorean identity, but they went around the elbow to get to the ear, I think. Okay, they start with the left-hand side because it's more complicated. That's exactly what we did. Sine squared was already fairly simple. Okay, it's already in terms of sines and cosines. Not much you can do with that. Okay? So what did they do here? They went to the same identity we did, but they said, what is secant squared with tangent squared theta plus 1, okay, minus 1 over secant squared theta. Yeah, that's perfectly correct. That's the Pythagorean identity, and you plug that in. But then you see that plus 1 minus 1 is 0, and you wind up, same thing we got as tangent squared theta over secant squared theta. Now express that in sines. Okay. Strange but true. They can do it this way. Rewrite secant squared theta as 1 over cosine squared theta, which of course this is in the denominator and cosine is the numerator. Okay? Then they take that tangent squared and write that as sine squared over cosine squared. Then they divide out the cosine squared and get sine squared. Yeah, that works too. Okay? It, to me, is a really convoluted way to do it, but it works. As long as all your steps are legal in most states, then you should be able to do them. Even if it takes you way around the world to get there, you can still do it. Okay? As long as all the steps are legal. So that was example 1, and that's equal to sine squared theta. Notice that you verify the identity by starting with the left-hand side, the more complicated side, using the fundamental trigonometric identities. That includes Pythagorean, ratio, reciprocal, any of those identities to simplify it until you obtain the right-hand side. So always, you can look across that equal sign to see which way you're heading, but don't cross it with an operation. Oh, boy. That was example 1, and they're done, okay? That's not very fair, is it? Let's do, they've only got examples 2, 3, 4, 5, 6, 7 to go. They only did 1. The easy one, of course. So let's just do the rest of them. Example 2. Let's go back to dark. Okay. Verify this one. 2 secant squared alpha, I can't write, is equal to 1 over 1 minus sine alpha plus 1 over 1 plus sine alpha. Okay? That's the one we're hoping to verify. We don't know if this is true, so I put the question mark there. It does a couple things. It keeps me from crossing it. I can't jump over the question mark. No. Okay. Now, here I'm going to break with their rules. Okay? I want to work with both sides at once. Number one, I don't like secant squared by themselves that much. So I want to write that in terms of sines and cosines. So what would that be? 2 over cosine squared alpha, right? Is that right? Okay. So that's legal to do on that side. I have across the thing. The question is all this stuff on the right-hand side don't equal that? It doesn't look very promising right now, does it? Okay? Now, what can you do to simplify that right-hand side? Any ideas? Basically, those are two fractional forms, right? How do you add fractional forms? Common denominator. And what would that common denominator be? It's just the product of the two, because there's no way to tell, if there's any common factors. I would think not, So basically, it's the product of those, okay? So in other words, we're going to have to multiply this one by 1 plus sine alpha, right? But if we do that, we also have to multiply the numerator by 1 plus sine alpha, right? And we have to multiply this one by 1 minus sine alpha, right? And that means we multiply this one by 1 minus sine alpha. Okay? Got it? Okay. Now, we have a common denominator. What does that common denominator happen to be? I know it's the product of those two things, but what is the product of those two, or those two? They're the same thing. Most of the time, I leave it in factored form. This time, it's going to make sense to do something with that. 1 minus sine squared theta, alpha. Yeah, okay. So what we have in the numerator is a 1 plus sine alpha. Okay, and this is 1 minus sine squared alpha. And this is plus 1 minus sine alpha over 1 minus sine squared alpha. Right? But you have the same denominators, right? So you could add the numerators. And what does that give you? 1 plus 1 is 2. And sine alpha minus sine alpha is 0. Right? So that numerator adds to 2. What does that denominator? You have 1 minus sine squared alpha, but what does that ring a bell? Squared alpha. I can't write. Okay. What is that? That's not cosine squared alpha. And guess what we have? 2 over cosine squared alpha is equal to 2 over cosine squared alpha. Yay! Done. Finished. We didn't cross the equal sign, but sure enough, we made that side equal to this side. We changed things on both sides, and there's no reason to stop and do them separately. You do them as you go. So you see how that worked? Really nicely. Okay. And if you see how they do it, they get down to this stage and then go back and say that's the same as 2 times sine squared, secant squared alpha, which is fine. Now remember, every one of these has a checkpoint. The checkpoint has audio-video solutions at larsonprecalculus.com. All right. So let's go to example 3. Can I erase this one? Okay. These turn out being fun even, don't they? Okay, sort of like a puzzle. I've always liked puzzles. verify this identity. Okay? Tangent squared x plus 1 times cosine squared x minus 1, they claim is equal to tangent minus tangent squared x. Okay? Now, any thoughts, approaches, guesses? What might you do first? Any ideas? What's that? Okay, yeah, these have squares in them, so I would begin looking maybe at Pythagorean identities. Okay? Now, tangent squared x plus 1, is that a Pythagorean identity in itself? It's what? It's secant squared theta is exactly what it is. So let's try that first. Secant squared x. Now, how about cosine squared x minus 1? That kind of looks sort of familiar, but, okay, not quite. It's minus sine squared. Because 1 minus cosine squared x is sine squared. So this is the opposite of that, so that would be minus sine squared. So this becomes a minus sine squared x. Okay? All right. We still got problems here, don't we, Houston? Okay? Now, these two sort of, yeah. Yeah, 1 over cosine squared. That sounds like a capital idea. Get things in terms of sines and cosine. 1 over cosine squared x times a minus sine squared x. And guess what that gives you? Second? That gives you negative tangent squared x. You got it. Because sine squared over cosine is tangent, minus sine makes it minus, and that gives you this. Okay, so now we can truly say they are equal to each other. Now, if you wanted to, you could have made this up here minus sine squared over cosine squared, and then when you got to here, you're done there. So you can either work both sides at the same time, just don't cross that equal sign, but work with them individually, or get it this way. Either way is fine. I'm pretty sure the book did it your way, the first way you did it. Okay? That was example 3. Can I delete it? Okay. Sorry about the yawning, folks. I'm just fatigued to no end. And yeah, I had a treatment last Friday, and it sure seems like every time Tuesday is my worst day after the treatment. Saturday I felt okay. I mean, a little tired, but not too bad. Sunday was maybe a little tireder. Yesterday, beginning to feel it worse, but the day is so full. And then too, daylight saving time hasn't helped it at all. Okay, not a bit. But, okay, let's move on to example 4. And they're suggesting we do what we've been doing all along. Here's verify this identity. Tangent x, cosecant x, they claim is secant x. Okay? How would you go about verifying that, seeing if indeed it is true? Now, the first 3 examples, if you notice that, all had squares in them. And somewhere along the way, we used Pythagorean theorem. This one no squares. So probably not going to use Pythagorean theorem, at least to begin with, or Pythagorean identities, okay? So what might you choose otherwise? What's my favorite? Get everything in terms of sines and cosines. So let's start with the tangent x. What would that be? Sine x over cosine x. What's cosecant x? 1 over, what do you say? Sine x. Okay. Now, I kind of like to do both sides, so let's do the right-hand side. We'll get that in terms of sines and cosines too. What does that give you? 1 over cosine x, right? But what do you notice happens on the left? The sines divide away. And you're left with 1 over cosine equal 1 over cosine. Got it. See how it works? Pretty straightforward and fun. And almost sort of easy. Okay? How about this one, though? Here's the B part of example 4. Tangent x plus cotangent x supposedly is equal to secant x cosecant x. Okay. Again, no squares here that we see so far, so Pythagorean identities are not very useful. So what would be your guess? First step. Second? I can't hear it, sorry. Yes, I'd get everything in terms of sines and cosine. What's tangent in terms of sines and cosine? Sine x over cosine x plus, and what's cotangent x in terms of sines and cosine? Cosine x over sine x. It's exactly the reciprocal of tangent. And the question is that equal to what's secant x? One over cosine x, and cosecant x is 1 over sine x. Okay. Goodness gracious. I am so tired. Okay. Now, multiplying fractional forms are pretty straightforward, so you don't really have to do anything there. I'm going to leave that alone for now. But adding or subtracting, yeah, you got to do something else. What's that? Common denominator. What's going to be the common denominator between those two denominators? Yeah, the product of the two. So to get the common denominators, you need to multiply this one by sine x. But if you do that, you also multiply the numerator by sine x, which makes it sine squared x, right? And to get this to be the common denominator, what do you got to multiply by? Cosine x. But if you do that, you have to multiply the numerator by cosine x, which makes cosine squared x. Okay, now we got our common denominators, which are sine x, cosine x, and sine x, cosine x. Okay? But we can write that just once. I don't know why I wrote it twice again, because we already had that. So let me, it didn't erase. Okay. Let's just write that common denominator down here once. Okay? Sine x cosine x. Okay? And what your numerator becomes? Sine squared x plus cosine squared x. And what does that happen to be? 1. 1 over sine x, cosine x, is equal to 1 over sine x cosine x. Done. Right there. They're the same. Okay. Now you don't have to do both sides. I like to do those. You know, that keeps me from having to do one more step on this side to make it look like the other side. See how it works? I don't know. Sorry. Didn't know the stuff had all gotten in the way. Okay, so there was for A and B. And again, there's a checkpoint at the bottom of the page, and it has an A and a B. Okay. Now, they should have at least put this slide on there. At the top of page 358, it says, recall from algebra that rationalizing a denominator using conjugates is, on occasion, a powerful simplification technique. Okay? But it's not just for rationalizing denominators. Rationalizing is if you have irrational forms. But, you know, multiplying by a conjugate usually makes things better. Give me a binomial, any binomial in the world. Make up a binomial. Give me either a number or a variable. I don't care which. Or both. Anything. X, okay. Plus or a minus sign? Minus. And give me either a number or another letter. 2. Okay. If you had an x minus 2. What is the conjugate of x minus 2? X plus 2. And what happens if you multiply them together? X squared minus 2x times x, wait, no, x squared minus 2x plus 2x, those add to 0, and then you get a minus 4, right? That's a pretty simple thing. You start with a binomial, multiply by a monomial, you still get a binomial, okay? Pretty easy to work with, okay? If this one had an irrational piece in it, like a square root of x, or a square root of 2, and you did that, then you would wound up with something with no square roots in it, because you're squaring both of those. If one of them had a complex thing, as in x minus 2i times x plus 2i, then you would wound up with x minus a 2i squared, well 2 squared is 4, I squared is minus 1, that would have been x squared plus 4. It would have had no more imaginary parts. It would have been all real numbers. And if it had been rational, a radical in there, you know, a square root, multiply them together, you lose the square root. So it's usually a pretty good idea to multiply by a conjugate if you think it's going to help. So sometimes that's going to work here too. So let's do example 5. Which is going to probably use that. Okay? Wait. I guess before we do that, yuck. Let's do 1. Let's say we start with a form like this. 1 over 1 minus cosine x. Okay? Now there's not much you can do with that, is there? Okay? I think I am going to erase some things. Probably should have cleaned my whole slide, but I didn't. So suffer through it. Okay. Now, if you can't think of anything else to do, multiply numerator and denominator by its conjugate. And what's the conjugate of 1 minus cosine x? 1 plus cosine x. But as long as you multiply and divide by that, that itself is 1. Multiplying by 1 doesn't change anything, right? Well, what does that give you now? The numerator is just simply 1 plus cosine x. The denominator becomes
1 minus cosine squared x. And what's 1 minus cosine squared x? It's what? Sine squared x. And there you just went from a, and here's how this has helped you. You may not think it has, but it has. You went from an expression that had the binomial in the denominator to an expression that has a monomial. Sure, it's a little more complicated, but it's something you can deal with. Okay? Now, if you wanted to, you could split this into 1 over sine squared x plus cosine x over sine squared x. Okay? 1 over sine squared x is what? Cosecant squared x. I don't particularly like, but it's okay. This one is, this thing right here is equal to cosine x over sine x, right? Times 1 over sine x, right? And that would be cotangent x times cosecant x. Okay? And what you did, you went from a fractional form that you can't do much with to something with everything in the numerator. Okay? It's still a little complicated looking, but at least you got everything on the up and up. Nothing down and on the up. Okay. So, let me erase all this now. I started too early. I should have, probably. Okay. Let's do example 5. Now, this one says see larsonprecalculus.com for an interactive version of this type of an example. So, if you don't like the way I do it or the way you see it in the book, you can interact with it at larsonprecalculus.com. So, whoa. How are we doing? Can we do it in 3 minutes? What you think? Give it a shot? Okay. Verify this identity. Secant x plus tangent x is equal to, or at least they claim it is, cosine x over 1 minus sine x. Okay? What do you reckon to do with that? Okay, the right-hand side is just begging you to multiply by a conjugate. Okay, so this will be 1 plus sine x over 1 plus sine x. Ooh, that's ugly. Okay, kind of ugly, but I've done it. Okay, now, you know me, what you think I would say do on the left-hand side? Yeah, I get it. Okay, and what would this be? 1 over cosine x plus sine x over cosine x. Hey, I think that's gotten a little simpler, don't you? Okay? Because this on the left now becomes 1 plus sine x over cosine x, right? Well, let's see what the right-hand side has become. If we multiply that out, what do we get? Now, I'm not going to multiply the numerator out. I'm going to leave it in factored form. Cosine x times 1 plus sine x, right? Over squared x. Perfect. Okay. Now, what does that become? What is 1 minus sine squared x? That's cosine squared x, right? Okay, well, a cosine goes into one of those two cosines, and what does that leave you with? 1 plus sine x over cosine x, which is exactly the same on both sides, so you're smiling about it, right? Okay. Yeah, isn't that fun and interesting? Enlightening? Yeah, well, we'll leave it alone. Okay. If you see how they did it, they basically do a lot of the same thing, though they, frankly, I think get it a little too complicated. You can keep it a little simpler, okay? But there is a checkpoint there. We will begin next time with example 6. We'll do example 6 and 7, but we will start at section 5.3 because there aren't any of these in 5.2. Homework exercises here will be any of the odds 9 through 17. They're all at Calc Chat. 9 is at Calc View. Any of the odds 19 to 23. They're all at Calc Chat. 21's at Calc View. Any of the odds 25 to 29. They're all at Calc Chat. 27's at Calc View. Any of the odds 31 to 35, they're all at Calc Chat. 33's at Calc View. And let's hold off there. We'll do the rest of those later. Okay? Enough to get you going. All right. Did everyone get the second test? You didn't. Okay? The rest of you did, right? And I can't remember. You did turn in the first test, too. So let me see if I found the second test for you. I may have just thrown it out because you weren't here. Just kidding. Test 1. Test 1. Ah! Looks like I might have test 2 somewhere here. Getting close. Here we go. Test 2. Now, do you need graph paper? Huh? You think you do? Okay, because they're like 9 to be graphed. You got enough? Or you want some? Okay. Now, I printed these both sides, so if you can do 2, 2, that would be 4. Now, these that come out as start, 2, 2, that would be 8. So on one of those pages, get 3. The other 3 sides, you can get 2, and you got it 9. Okay? If you need more, I got more, but I'm stingy. Okay. All right. Good deal. Any questions? Then we'll see you on Thursday, and I'll go on and close this one out.